What's something that computers are good for? Searching. Searching big lists. So, let's talk about searching with a regular computer and talk about searching with a quantum computer. Now, why would it be any different? Well, you know it's going to be a lot different or I wouldn't have this video going. Let's take a case of a large number of elements, and I'm going to choose 1024 because that is 2 to the 10th power. You have 1024 memory spots, and you want to find a value. Let's say 16. And so we use a computer to start searching for 16. Now, if 16 isn't in the list, then we'll search all 1024 elements and we won't find anything. Now, if it's in there, it's going to take us between 1 and 1023 searches to get to the end. But on average, it should make sense to you that it's only going to take, on average, searching half the list to find it. Sometimes you'll get it on the first one, sometimes you'll get it on the 900th one, sometimes you'll get it on the 512th run. But the idea is that you'll find that item in the list eventually. Now, what's different about a qubit system? Well, to store 1024 different conditions, we need 1024 different computational bases. And that would be 2 to the 10th power. If you have 10 qubits, then you can store 1024 items in that. Seems strange. You're only using 10 qubits, but you're storing 1024 items in there. So how do we search the qubit one? Well, that's tough to try and figure out. I puzzled over it for a long time before I could get to the point where I was actually willing to talk to you about it. Quantum computing topics are very abstract feeling. When you talk about a classical computer search, you just read the elements. So you're only reading one at a time. In a quantum computer search, you're examining all of them at the same time. 10 qubits at the same time? 1024 solutions at the same time? That's what's hard to put together up here. And it's not going to be a simple discussion. What is simple is that if it takes 512 runs for the average search of a traditional computer, it's going to take the square root of 10,024, which is 32 average runs to get the data that methodology. So for all the trouble that we go through, there's a huge advantage if we can make it work. Okay, searching. What's a typical thing you search in? Well, I'm going to use a phone book. A phone book with names, phone numbers, and the ability to have a number and find the name, kind of like a reverse phone book, or the name and find the number. So that's going to be our model for this whole thing. And we're going to start with classical view of this thing and then build that model so that we totally understand it, including me, which is really important, and then we'll move on to the next one. Before I cover the classical version of a phone book, let's look at the Grover ideas so we can have those in our head. 10 qubits for 1024 entries. The name and number and name, those are no different. What we look for is not the value, but the address of where this thing is. And there's going to also be something like an existence test so we don't search forever. Grover amplifies indices of matches. So what the Grover search is going to do is look at everything at once. That's one of the mysteries of the quantum thing, is it looks at all the entries at once, and then at each pass it amplifies which ones follow the target rule, which one follows the name, or which one follows the number. Here's what I want to do. I want to do the classical version, have that clearly in our heads, and then we'll actually at some point actually program the classical version and have ways of seeing how fast it searches and how many searches it has to do, and then we'll go through and do the Grover version that uses the quantum bits and the improved searching methods. And then at the end, our goal is to have two programs that compare each other and do all that. But before we get into coding, we have to understand what we're doing and do a pseudocode version of it so we can actually build the code and hope that it works the first time, or at least have much more guarantees in that area. So think of a classical computer. I think I can talk through this. Think of an unsorted list. That's the hardest to search for the classical version, and the classical version will just read one entry at a time until it finds what it's looking for. Now, how does it search for different things? Well, it's set up at the beginning to say search only the name entry, or search only the phone number entry to go through that. So we have to have a database which includes a value for each one of these things. So for each index, we'll have to have a number entry, and then we have to have a name entry. So it's going to be a fairly large number of memory locations to get all this to happen. Later, when we talk about the full implementation, we'll also talk about this thing called a hash search, which takes all these different strings. The names are going to be all different lengths, and it breaks them down into a single code that's much easier to search. So we'll actually use a hybrid version of this thing. We'll use a quantum computer and a classical computer, because the classical computer is really what we're writing the Python program in, and then we're calling on these special functions that will simulate the quantum computer. Here's a way of comparing these things. Classical linear scan. Check entries one by one. This thing cost, or time complexity, they've got an O here, and we'll see why that's an O later on. But anyway, up to 1024 checks if we're talking about a 2 to the 10 or 10 qubits. Classical binary search would divide and conquer by sorting the list. Now, if the list is sorted, which would be the way it would be in a phone book, either sorted by alphabetically on the name or numerically on the number, then this is what it's going to take. The log of n, or log to the base 10, and then it says it'll take you 10 trials to get to the actual item, which, wow, that sounds great. And then we have a hash table, which uses a hash index, which will give us on average only one check. So you think, wow, classical searches are better than quantum searches, because that quantum search is only the square root of n. So here, that doesn't look so great compared to this or this. But what if we don't have a sorted list? What if that's unavailable to us? That's when the quantum thing really takes off, because here we're going up to 1,024 checks, on average 512, and this is only going to take us 25 times through the list. Now that I've laid the groundwork, it's time for us to mentally get ready for building our Grover search machine, the Quantum Searcher. So this video only serves as an introduction to get your head on the right track. So please wait for that next video, which is coming very soon.